continuing our series of road trips along California's San Andreas Fault. This time we'll explore its very southern end, from the Salton Sea through the Coachella Valley and ending at the eastern side of the San Bernardino Mountains. If you've ever driven Interstate 10 or Highway 111 through the Coachella Valley communities of Palm Springs, Indio, and Mecca, you may have wondered how the landscape there, mainly the mountains, hills, and the Coachella Valley itself, was formed. Well, it's all San Andreas' fault. Keep watching and we'll explain the mechanics of how it happened and show you where to see the evidence and features that the San Andreas left behind. Our tour starts on the east side of the Salton Sea, simply because this is where the San Andreas Fault begins its 750-mile or 1,200-kilometer journey that trends northwest through California. The tour ends at the northwest corner of the Coachella Valley. We'll follow major highways and branch off onto side roads to see some of the noticeable features along the fault's path. Hopefully, you've seen one or more of our other videos about the San Andreas Fault, or are familiar with the way faults and tectonic plate boundaries work. If not, we strongly recommend watching our San Andreas tour near Wrightwood first, as it explains a lot of details that you'll see in this video tour. It's important to recognize that the San Andreas Fault is not just a fault. It's also a plate boundary between the North American and Pacific plates. Both plates are sliding past each other, with the Pacific plate heading in a northwestern direction and at a faster speed than the North American plate, which is going the opposite direction and moving much slower. It's also important to know that the San Andreas is a single fault and is also the main fault of the larger San Andreas Fault system. This system includes multiple branches or strands of the main fault itself, and even though they're part of the San Andreas system, some of them are named separately here in the Coachella Valley region. Those names you'll hear are the Mission Creek Fault and the Banning Fault. It's also good to remember that most faults are not just a crack or straight line in the ground. Many are fault zones of anywhere between 1/4 to a mile wide, as you may have learned in our other videos. Although the San Andreas has its southern end near the Salton Sea, the plate boundary itself continues southeast for many hundreds of miles, forming the Gulf of California and separating Baja California from mainland Mexico. In this area, the plate boundary is now a pull-apart basin and isn't referred to as the San Andreas Fault. Because the fault transforms from strike-slip to a pull-apart action at its southern end, an unusual geologic feature occurs here that doesn't occur anywhere else along the San Andreas. They're called mud volcanoes and occur randomly near the fault on the Salton Sea's southeastern corner. We'll visit a few of these bubbling mud pots. You may remember from our other San Andreas Fault tours that we run into many what are called sag ponds. Since the Coachella Valley is all desert, we won't see any of those. There simply isn't enough water near the surface here to create such ponds. Plus, even if they did form, the water would quickly evaporate. Instead, we'll see a number of palm oases. These California fan palm trees grow abundantly where water has been dammed up by the fault boundary and created springs. Because of this, you'll see how these palm trees literally mark the location of the fault in many places. As the fault crosses both barren desert and developed land between the towns of Indio and Desert Hot Springs, we'll visit places where the fault has made its mark on the land. We'll point out these places in the video so that when you visit yourself, you'll know exactly what you're looking at. If you do plan on taking this tour yourself, do not visit in the summer. Temperatures here easily top 115 degrees Fahrenheit or 46 degrees Celsius on a regular basis in July and August. That wouldn't be fun exploring weather. Before we get started on our tour, let's first talk a little bit about how the Salton Sea and a big dune field to the east, called the Algodones Dunes, as well as the Coachella Valley itself, was formed. It's quite an amazing story, and the way it was formed was all San Andreas' fault. This amazing story includes how those sharp and rugged mountains on the west side of the Coachella Valley, the San Jacintos, also pronounced San Jacintos, and the Santa Rosa Mountains were abruptly uplifted and created. If you visit Indian Canyons south of Palm Springs, either Palm or Andreas Canyons, you will see the sharp and angled uplift of these mountains that have their base around 400 feet or 120 meters and top out at just over 10,000 feet or 3,000 meters. It's quite a sight to behold with the desert flora against these sharply angled rock formations. This story also includes how the expansive agricultural area just south and east of the Salton Sea, known as the Imperial Valley, became very fertile and is now rich farmland. As you might guess, this too was San Andreas' fault. Similar to how the San Francisco Bay Area was formed from strike slip action on both the San Andreas and Hayward faults, causing the land between them to be spread apart. So much so that seawater flowed in and created the San Francisco Bay. The same strike slip action between the San Andreas and faults to the west, mainly the San Jacinto and Imperial faults, created a large flat and low valley. With or without water, this valley is known as the Salton Trough. Geologists refer to the trough as a tectonic pull-apart basin, also known as a graben. Keep in mind that the Salton Sea we know today was created in 1905 when an irrigation canal broke and diverted all the water from the Colorado River for 2 whole years into the dry Salton Trough. In reality, the Salton Sea was accidentally created by man. Before the Salton Sea formed, it is said that the Salton Trough was once the lowest point in North America. Now that water flooded the trough, that distinction belongs to bad water in Death Valley at 282 feet below sea level. Before there was a Salton Sea, there was prehistoric Lake Cahuilla. Over the past million years or so, it formed, then disappeared many times. Around the year AD 1400, Lake Cahuilla was estimated to be 25 times larger than the Salton Sea. By 1800, before the canal broke, it was completely dry. The reason why Lake Cahuilla filled with water, then drained so many times, is not San Andreas' fault. It was the Colorado River's fault. For as long as it existed, the Colorado River would alter its own course frequently due to a natural process known as river meandering. Sometimes it flowed into the Sea of Cortez, like it does now. Other times it would meander for a few years, flowing into the Salton Trough and filling up Lake Cahuilla. By the way, the Sea of Cortez is the same as the Gulf of California. Of course, today, much of the water from the river is diverted into aqueducts, with much of it going to Southern California and not into the Sea of Cortez. But that's another story for another day. As you probably know, the Colorado River was partially responsible for creating places like the Grand Canyon in Arizona, or even canyonlands near Moab, Utah. The sediments that the river eroded away from these places and transported down south would be deposited into the Salton Trough at times when it was filling Lake Cahuilla. It's those sediments, rich in nutrients, that created the fertile lands of Imperial Valley. During different stages of sediment deposition, other places nearby were formed, such as the Badlands of the Anza Borrego region, and the Painted Hills with similar badlands, a place we'll visit on this tour. There are accounts of, or maybe it's a tall tale, of a Spanish galleon venturing into Lake Cahuilla when it was full of water in 1615. It was laden with riches when it became stuck in the shallow water. The crew walked away, and the ship was eventually swallowed up by the desert after the lake dried up, only to reappear a few times during big dust storms. If this was actually true, it's an example of how big this body of water was and can still be because of the tectonic action of these faults, influenced by the San Andreas, stretching and lowering the Earth's surface, which allows for this water to accumulate, just like in the San Francisco Bay. So now let's talk about how the Algodones Dunes were created. During the periods when Lake Cahuilla was dry, the surface sediments were blown east by steady prevailing winds from the ocean. A strand of the main portion of the San Andreas Fault that we'll visit shortly extends southeast from the town of Niland and formed a mountain range on its east side called the Chocolate Mountains. Today's Union Pacific Railroad tracks roughly follow this fault strand. These mountains blocked the winds and dumped the airborne sand where you see it today, creating the sand dunes. And so, thanks to the San Andreas Fault creating this giant sandbox, hundreds of OHV riders have somewhere to play. Incidentally, as you can see, this huge dune field extends way down into Old Mexico. Okay, let's get going. We're going to travel south on Highway 111 to begin our tour on the southeast side of the Salton Sea, near the town of Niland. Using your favorite navigation device, we personally use Google Maps on our phone. Navigate to McDonald Road and Davis Road in Niland. This intersection, 4 miles southwest of Niland, is in a very remote area near the southeastern corner of the Salton Sea. Nearby are a couple of geothermal power plants that are harvesting hot water from deep below the Earth's surface. Those power plants are actual evidence that something interesting is going on here. When you drive near these plants, you'll see big pipes running in different directions. These pipes transport the hot water from surrounding wells to the power plant. As mentioned earlier, because of the surface spreading that's going on in the Salton trough, heat from inside the Earth is seeping through cracks up to the surface. With all that Colorado River water that's been seeping down and accumulating over the centuries, there are pools of hot water deep below. Some of that hot water mixes with dissolved gases, like carbon dioxide and methane, builds up pressure and makes its way to the surface with its muddy payload. It then erupts at the surface, creating these miniature volcanoes. These mud volcanoes move frequently. The ones just to the south of the geothermal plant on Davis Road were erupting constantly a few years ago, but are now dormant. New volcanoes began erupting about 1.5 miles west of here, near a place called Red Island Volcano. New volcanoes pop up frequently, so if you want to see one in action, you'll need to do a little research. Over the past few decades, around 30 mud volcanoes have been identified. Interestingly, many of them are along a strand of the San Andreas, probably because that superheated mud and gas is following the cracks created by the fault. Next, navigate to Davis Road and Highway 111. The next volcano we'll visit is called the Niland Geyser, which is another mud volcano. It's also known as the Moving Mud Pot. This mud pot is easy to visit, simply because it's literally on top of Highway 111. In fact, it caused the highway department to alter the course of their road, which is evident by all the barriers you must drive through on the detour around the mud pot. The Union Pacific Railroad was also forced to move their tracks as the mud pot was undermining its tracks as well as the highway. Numerous gas and communication lines also had to be moved. Here's a panoramic view of the site. Here's the junction of Davis Road and 111. Here's where you can park and see the mud pot. And here's the mud pot. You can see the various railroad tracks that the Union Pacific was moving. The San Andreas heads southeast here towards Algodones Dunes. The volcano actually formed in 1953, but it was a distance away from its current location. It then began moving to where it is now. In 2018, it moved 20 feet. In 2020, it moved 10 feet per month. At the junction of Davis Road with Highway 111, you can pull in and park between the highway and railroad crossing to take a closer look at the bubbling mud pot. As you look more closely into the mud pot to see it in action, use caution. In addition to the mud pot being obviously very hot, it also expels a lot of carbon dioxide, which could cause you to suffocate if you were to fall in. And who knows how deep it is, too, so be extra careful. Seeing a mud pot up close is kind of fun, but seeing a train go by a bubbling mud pot is really unique. Go to your favorite search engine and look up Niland Geyser to learn more about this fascinating little geologic feature, thanks again to the San Andreas Fault. Continuing north on Highway 111, the San Andreas Fault roughly follows the eastern shoreline of the Salton Sea. About 1 mile east of the turnoff to Bombay Beach, the fault crosses the highway. As you can see from this panoramic shot of this area, there isn't much evidence that the fault exists. The reason it can't be seen is because it's buried by all the alluvial fans and previous sediments deposited during incursions of ancient Lake Cahuilla. Who knows, we may be standing on soil that once filled Zion Canyon in Utah. Unlike other places along the San Andreas, such as offset stream beds that mark the fault's spot, there's nothing like that nearby to mark the fault's location. But we'll see more evidence of the fault's existence at our next stop. Navigate now to Box Canyon Road and Painted Canyon Road. The route to this intersection will take you off Highway 111 through some orchards and farmland and onto 66th Avenue heading east, which turns into Box Canyon Road. The Mecca Hills are seen in the distance. Painted Canyon Road is a 4 3/4 mile long out and back road. It's a bit rough and not recommended for sedans. Vehicles with high clearance should be used, but four-wheel drive isn't necessary. The road leads us to its namesake, Painted Canyon. For the first 2 miles, the road parallels the fault, which is near the base of the colorful Mecca Hills. The road then turns east and enters Painted Canyon. You will cross the fault in just under a mile after turning east. There isn't an obvious crack in the earth here to mark the fault line, but these tilted rock layers are evidence that it's here. This is an aerial view where the fault is located on the left or north side of the road. According to the fault line on the Gaia GPS map, it follows roughly this line. You can see how layers are tilted at a shallower angle here, but on the other side of the fault, they're tilted at a much steeper angle. Much of the radically tilted layers were caused by the action of the San Andreas compressing and squeezing the Mecca Hills against other parallel faults to the east. This squeezing action literally crumples the ground into what we see today and what are commonly referred to as badlands. We'll encounter badlands later in our tour at the Indio Hills near Thousand Palm Oasis. There's also the Borrego Badlands located 25 miles southwest of the Mecca Hills. They were created from a similar squeezing action between the Clark and Coyote Creek faults, which are part of the San Jacinto Fault Zone near the town of Borrego Springs. The further you drive up Painted Canyon, the more interesting the canyon gets with all its twisted geology. Right about now, you'll also discover how the canyon got its name, with all the warped, multicolored layers, all caused by the squeezing action of the San Andreas. The different colors are caused by the variety of minerals in each of the layers that have now oxidized. At the end of the road into Painted Canyon is a trailhead where several trails lead you into this interesting landscape. Here's what we saw when we followed the main part of the canyon for a mile. The canyon walls are near vertical, and since they are mostly composed of mudstones, you'll find the phenomenon of what's called wax drippings. These are created when wet mud drips down the sides of the canyon walls and then dries. Hiking further up the canyon, you'll also see where the layers become flatter, rather than the vertically tilted layers we saw earlier driving up the canyon. The further you continue hiking up canyon, the narrower the canyon gets. The hike is a wonderful experience and a great way to see the inside of these heavily warped hills. When you're finished with Painted Canyon, return the way you came in. But before heading west back towards Highway 111, you might want to take a short side trip up Box Canyon Road. This is a good alternative if you don't have a four-wheel drive vehicle, but still want to see the twisted geology. Just as the road enters the canyon, about a half mile from the Painted Canyon turnoff, the San Andreas crosses the road. Unfortunately, there isn't much evidence of the fault being here other than the Badlands. Continue further up Box Canyon Road to see more warped and unusual scenery. If you decide to pull off the road for a closer look, just remember there's deep sand just off the pavement and you could easily get stuck. When you're finished looking around, turn around and head back to Highway 111 as mentioned. From here, we'll navigate to the golf club at Terralago. If you've watched our video on touring the San Andreas Fault through San Bernardino, then you would have seen how much the fault cuts through normal neighborhoods. Other than some long and narrow parks, or the former sag ponds that have been turned into decorative lakes, you wouldn't know the fault is there. The same is true for a golfing country club and resort that's located near downtown Indio. Terralago is also located next to the World Mark and other popular resorts. Just before reaching the golf club, the road crosses over a canal. This is the Coachella Canal. It brings water from the Colorado River to the communities in the Coachella Valley, such as Palm Springs, Cathedral City, and Palm Desert. Let's take in a panoramic view of this area. Here's the bridge over the Coachella Canal. Panning to the left, over here, is the San Andreas. If we cross the bridge and turn left, here's a straight view down the golf course. This green area in the saddle in the distance is the fault line as it heads northwest and in the direction of where our tour is going. Finally, here's an aerial view of this area. There's the bridge over the canal. Here's the town of Indio in the foreground, with a sweeping view of the Coachella Valley in the background. Panning to the right, we see the golf course fairway we saw before, and here's the fault line. We'll pan 180 degrees around to look at the fault line in the other direction. Here's the canal and the fault line heading towards the southeast. Okay, enough of earthquake faults and golf courses. We'll exit the same way we came in. Our next stop is the Coachella Valley Preserve. But before we do that, let's take a quick detour onto Coyote Song Way. At the end of the road is near where the San Andreas Fault splits into two different strands, the Mission Creek Fault and the Banning Fault. When we use Google Earth to fly from our last stop at the golf course to Coyote Song Way, you can clearly see the trace of the San Andreas. But as we approach Coyote Song Way, which is here, you can start to see the two fault strands. On the right is the Mission Creek, and branching to the left is the Banning Fault. We'll continue flying above both faults to our next stop, the Preserve, which is here. The two fault strands seem to encircle the Indio Hills, which are badlands similar to the Mecca Hills. Later, we'll use Google Earth to see how these two fault strands join up again at the beginning of our San Andreas tour through San Bernardino near the town of Oak Grove. Back to the end of Coyote Song Way, you're now looking at an aerial panorama of this area, starting with looking back southeast towards the Terralago Golf Club. As we pan to the left, the fault hugs the base of the hills. Somewhere in here, the fault splits. In the distance, you can see the palm trees of the Coachella Valley Preserve. Behind it are the Indio Hills. Finally, way in the distance, you can see Mount St. Gorgonio, Mount San Jacinto, and the upper reaches of the Coachella Valley. And here is Coyote Song Way. All right, now our next stop really will be Coachella Valley Preserve, which is also known as Thousand Palms Oasis. Using Google Maps, navigate to either of those names. Here, we're floating northwest along the Mission Creek Fault. This is Thousand Palms Canyon Road, and here is the Coachella Valley Preserve. This is truly a great spot to study both of the fault strands because, thanks to the various palm tree groves, they really do point out the fault line. Here's a panoramic sweep over the small preserve. If you plan to visit, make sure to check the days and hours it's open, as it's not open every day. Walking through the palm trees makes for a unique experience. When the preserve is open, after walking past this gate, kiosks explain details about the Oasis and the San Andreas Fault. There's also this sign that points out right where the Mission Creek strand sits. The walk through the preserve on the boardwalk will provide a great experience of exploring a very dense stand of date palms. Like other oases, the fault trapped underground water here that has bubbled up to the surface. To get a better view of the faults, find the Pushawalla Trailhead, which we floated over earlier. Follow the signs and you'll soon be following this trail. You can see the trail climbing this ridge. On the ridge, looking back at the trailhead, you can again see a good view of the fault line without the help from hitching a ride from a bird. It seems that we're standing right on top of the fault. This is the view from the ridge looking in the other direction. This fold at the bottom of the ridge marks a path of the Mission Creek Fault. Continue on the trail as it straddles the ridge for more views of the fault. In the distance below, you can see more palm trees. Remember the folds we just saw? These trees mark the continuation of that line. Looking ahead of the trees, you can see another linear gulch, which could also be the fault. Notice too how these hills are similar to the Badlands of Mecca Hills. This again is the view looking back towards the Pushawalla Trailhead. Now let's explore the Banning Fault Line. Navigate to Willis Palm Trailhead, just down the street from Pushawalla. The trailhead is easy to find. Here's a view from above at the trailhead. Over here is where we climbed that ridge to see the other fault. The Banning Fault comes from this direction. Here's Coyote Song Way over here, and here's the golf club way in the distance. As in the previous scenes, the fault follows the base of the hills, which here is basically the hiking trail we'll be following in a moment. This is a drainage coming out of the Indio Hills. And here's where the Willis Palm Grove starts. Like all the other palm tree groves we've seen marking the fault line, these California date palms grow here because the fault brings water up to the surface. Here's another aerial view of the fault and the trail to Willis Palm Grove. Willis is just one of many palm groves that mark the locations of each fault. You can also see the trace of the Banning Fault as it heads along the base of the Indio Hills and all the way into the distance towards the fault's namesake, the town of Banning. Over here is Palm Springs, at the base of Mount San Jacinto. The hike to Willis Grove is easy. As mentioned, the trail is basically on top of the fault, and it's only half a mile to the grove. The embankment that the trees are growing on is essentially a scarp of the Banning Fault. Here's a sweeping view from the base of the scarp. The trail soon climbs the scarp into the palm trees. Follow it as it twists and turns through the trees to get a good sense of what it's like to be inside a palm grove. You'll see a variety of trees of all ages and sizes. Many of the taller ones are black after being singed from small natural fires that have occurred over the years. When you're finished exploring the grove, return to your vehicle using the same trail you hiked in on. Next, we're going to head over to the town of Desert Hot Springs. We're now going to visit those two fault strands as they both head further northwest. So navigate to Palm Drive and 20th Avenue. This intersection is about 1.5 miles from the Interstate 10 exit. This intersection marks the spot where the Banning Fault crosses Palm Avenue, a busy road between Palm Springs and Desert Hot Springs. Panning through the intersection from southeast to northwest, you can easily see the density of vegetation that's growing in somewhat of a line. Plus, if you look closer, you can make out a mound or small linear ridge that trends in the same direction as the vegetation. This is a fault scarp created by the Banning Fault. From the air looking southeast at the intersection, here's the fault scarp, and you can see the fault as it heads towards the Indio Hills. The fault bends here slightly to the right as it wraps around the southern edge of the Indio Hills to our last stop. Here's another view from the air, this time heading northwest from the intersection towards Mount San Gorgonio. Even though there's a lot of desert sediment and alluvium that has covered the fault, you can definitely make out its path. Using Google Earth, we'll orbit higher around the intersection. Now you can really make out the fault line. Looking to the west, you can see the fault heading towards the Banning Pass. We'll continue orbiting to the southeast, where you'll see the fault hug the Indio Hills, as seen from the Palm Drive intersection. Desert Hot Springs is another resort community north of Palm Springs. The reason for the hot springs being here is because the two faults trap pools of water nearby, where they are heated by underground actions, similar to what we saw at the beginning of our tour. Again, using Google Earth, we can see a line of vegetation right here. This again is the Mission Creek Fault. Right here is a rather large fault scarp along Mountain View Road. Here's a closer look at it from the drone next to that same road. The view is to the northeast. This is the only place where a large scarp like this is evident along this portion of the Mission Creek Fault. This is a perfect example of how strike-slip faults randomly create various features like scarps, linear valleys, and shutter ridges at various locations, as the two plates slide past each other. In this case, the raised portion on the North American plate is a bisected hill. The other half of the hill is on the Pacific plate and has slid northwest for a long distance and may either still exist there or has since eroded away over time. And for comparison, from the ground, here's how it looks when driving Mountain View Road, going north through and over the fault scarp. You can see the scarp is around 100 feet high. It looks a lot different from the ground than from the air. This is another view of the fault scarp, with a house sitting on top of it along Dillon Road, just east of Mountain View Road. Let's head back to Palm Drive and turn north to the heart of Desert Hot Springs. Navigate to Two Bunch Palms Trail and Verbena Drive. In this view, we're looking southeast again towards Indio Hills, which is here. The fault passes this way. Here's where that scarp is located at our last stop on Mountain View Road. Notice here the increase in vegetation. Now let's pan to the left. Up here are the Little San Bernardino Mountains. On top and behind them is where Joshua Tree National Park is located. Here's Two Bunch Palms Trail. And now you can make out the fault line by the difference in vegetation. The edge of the green vegetation marks the line of the fault as it heads northwest into downtown Desert Hot Springs. From Desert Hot Springs, the fault skirts the southern edge of the Little San Bernardino Mountains, which you can see here, and then over the San Bernardino Mountains about here. We'll continue our tour in this direction by navigating up to Mission Lakes Drive and heading towards Highway 62. Along the way, we'll pass by the Mission Lakes community. This low spot here is where the fault crosses the road. Now on Indian Canyon Drive heading towards Highway 62, we parallel the fault's path here at the base of the mountains. In the distance, you can see the fault's trace here, then further here as it cuts through a ravine next to Mount San Gorgonio. Approaching the traffic signal at Highway 62, we can see a closer view of the fault climbing towards Mount San Gorgonio, which eventually connects to the main strand of the San Andreas near San Bernardino. Again, with Google Earth, we'll follow the fault from this point and fly over the San Bernardino Mountains. You can see it head up this linear canyon, cross the saddle we saw in the distance from the traffic signal. Then it crosses to the other side and drops down into yet another linear canyon as it continues heading northwest into the San Bernardino area. All right, now to the next stop. From that traffic signal, head south on Highway 62 and navigate to Painted Hills Road and Worsley Road. Head south on Worsley Road, a short distance to a small downhill portion. This is the road crossing the Banning Fault. Looking back is this view of the fault scarp and the wind turbines in the background. Panning to the right, we can see where we came from. Here's the Indio Hills. Looking the other direction, we can see the fault cut through this ridge on the other side of Highway 62. We'll now switch to Google Earth to view the Banning Fault as it passes through this area. Clearly, you can see the various scarps and ridges created by the fault, like what we saw earlier along Palm Drive. As we continue floating west over the fault trace, notice all the vegetation growing here thanks to the increase of water in the Whitewater Canyon drainage that's trapped by the fault. We'll make a quick visit to this canyon by taking the Whitewater exit, which is exit 114 from Interstate 10. Navigate to the Whitewater Preserve. About 1.5 miles up Whitewater Canyon Road is the small hamlet of Bonnie Bell. The cluster of vegetation here, complete with an oasis of palm trees, marks the spot where the fault intersects the canyon. This is also the location of the Bill Havert Whitewater Preserve, not to be confused with the Whitewater Preserve found at the end of this road. This panorama of the canyon at Bonnie Bell shows how the Banning Fault cuts across the canyon. This drainage on the east side that's cut deeply into the ridge is the fault. From Whitewater, as we follow the fault's trace west along the northern side of the San Gorgonio Pass, we see more ridges and trenches marking the fault line as it heads towards the town of Banning. The fault then turns right, or northwest, towards the town of Oak Glen to connect to the main strand of the San Andreas. See our video tour of the San Andreas Fault through San Bernardino to continue this journey. And that sums up our tour of how the San Andreas Fault System shaped the Coachella Valley area and the surrounding mountain ranges. But before we go, there's one more thing you should see via Google Earth. And that's how these two fault strands meet up again before entering the San Bernardino area. From high above the western edge of the Coachella Valley, here's our last stop along the Mission Creek Fault at that traffic signal on Highway 62. And here's our last stop on the Banning Fault at the Whitewater Preserve. The Mission Creek Strand, which is more traceable here, cuts through the San Bernardino Mountains, creating the linear canyon where the community of Forest Falls is. It then turns into the Mill Creek Fault that parallels the San Andreas Fault about 1.5 miles to its north. Both the Mill Creek and the San Andreas actually connect near where they both cross the California Aqueduct near Devore. Now let's gain a little more altitude above this area so we can get a better view of the San Andreas to the northwest. You can now see the Cajon Pass and Lone Pine Canyon. Hopefully you've already seen our tour of the San Andreas through Wrightwood to better understand that section of the fault. Beyond Wrightwood, you can see how the San Andreas created the natural boundary between the San Gabriel Mountains and the Mojave Desert. We hope you've enjoyed our tour of this segment of the mighty and infamous San Andreas Fault. We also hope it has given you a better sense of how the various pieces of a puzzle formed to create the current landscape puzzle we now know as Southern California. And we use the word current because, after all, these faults are still moving and will be constantly changing the landscape here for eons to come. If you're curious about the other pieces of the Southern California landscape puzzle, check out our other video tours about the San Andreas and accompanying faults like the San Jacinto. Just search for San Andreas Fault, Back Roads West. Until you join us on our next tour, we bid you happy exploring.